Hey there. Here's an algebra question that was puzzling mathematicians in the 1600s, and I'm going to outline how Isaac Newton from England described his own original solution to this puzzle. Mathematicians were interested in this question because in Newton's time they were keen on investigating the rates of change of various quantities. For example, say that the temperature of some object is T squared, where T stands for time, and we wish to calculate how quickly the temperature is changing at a specific time, say x. Then we can evaluate t squared at x, and at a slightly later time, x plus h, as if we let a small amount of time h pass after our first measurement. Now we can algebraically calculate the rate of change of the temperature if we divide the change in temperature by the change in time, and the change in temperature would be x plus h, which is the time of the second measurement squared minus the time of the first measurement x squared over the change in time, which is h. Now this algebra is no problem. We can expand x plus h, we can collect like terms to get to the next to last step, at which point we can cancel h, and then at the end we can imagine h getting smaller so that we are calculating more and more accurately the rate of change of the temperature between time x and a very small time afterwards, and conclude that at time x the rate of change of the temperature is 2x. Now if you've studied the derivatives of functions, then this process is very familiar to you. Now we run into algebraic trouble if we replace the exponent on t, the 2, with a fraction like 1/2. Nothing changes about our strategy, but in this first step, these exponents of 2 would become 1/2s. And then attempting to algebraically move from the first step to the second step is, on the surface of it, impossible. So Newton, among other people, attempted to explain how we could expand an expression like x plus h to the 1/2. If we make a table with just the coefficients of the expansions of binomials like x plus y to whole numbered powers, we get the so-called Pascal's triangle, which features an additive property that works like this. Take the sum of any two numbers that are side-by-side neighbors, for example 4 plus 6, and that sum will appear underneath the right-hand neighbor. As another example, here 20 plus 15 is equal to 35. This additive pattern works throughout the table, and Newton attempted to find an algebraic way of capturing that pattern so that he could apply it to rows that might appear in between the existing rows of Pascal's triangle. In other words, Newton's goal is to find the expansion of x plus y to the 1/2, which would fit here in the table. He's trying to calculate the coefficients in that expansion. It's a mystery as to how many there even are. There's 1 in the expansion above and 2 in the expansion below. How many are in the expansion of x plus y to the 1/2? That itself is a mystery. So, Newton algebraically encoded the additive pattern that these numbers exhibit and planned to apply the resulting algebraic template to rows like the one associated with x plus y to the 1/2. First, here's how he encoded the additive pattern. Take a look at this block of numbers. Let's replace the 6 with a variable, like, say, a. Now we're tempted to replace 7 with a plus 1 to preserve the additive pattern, but look up here. If we put zeros in the blanks, which does preserve that pattern, the additive pattern, for example 1 plus 0 equals 1, then it's clear that this gap from 0 to this unknown coefficient and then onwards can't be 1 anymore. In fact, it looks like it might be a half. With this in mind, Newton replaced all of the entries in the first column with a new variable, b. So in this block of numbers, all of the 1s would be replaced with b. Now we can try to preserve the additive pattern, for example replacing the 7 with b plus a. I'll write it as a plus b alphabetically, and then the 8 would get replaced with b plus a plus b, or a plus 2b. And we can even work backwards. This 5 needs to be replaced with something so that b plus it will equal a. So of course we need the a there, but then we need to subtract b so that the b's will cancel. And similarly, to replace this 4, we need b plus whatever's in the blank to equal a plus b. So we need the a, and then we need to take away 2b to get the minus b. Now think of this block of algebra like a template or a recipe card that we could slide up to cover the top rows of this table. Every b in the first column of the recipe card will cover a 1 at the top, so it seems clear that this number here, which would be the first coefficient in the expansion of x plus y to the 1/2, should be a 1. But in the second column, a minus 2b will cover the 0. A minus 2b then must equal 0. The a minus b, the second entry down, will cover this question mark. So a minus b will equal the question mark, which will be the second coefficient in the expansion of x plus y to the 1/2. This a will cover this 1. So a is equal to 1. And now we have a little algebra problem to solve. If a is equal to 1 and we substitute that into the top equation, we have 1 minus 2b is equal to 0, which has the solution b equals 1/2. And then to find the question mark, we can substitute 1 for a, 1/2 for b, and subtract them to get what the question mark equals. So the second coefficient in the expansion, Newton guessed, was 1/2. That makes sense because the gap then from 0 to 1/2 and 1/2 to 1 would be consistent. Now to find the third coefficient in the expansion of x plus y to the 1/2, we'll pull the same trick on the third column of our recipe card. Let's replace this 15 with the variable c. Like before, we want to preserve the additive pattern, so this 21 would be replaced with a plus c. Here are the rest of the appropriate entries, all of which follow the additive pattern. For example, a minus b plus negative a plus b plus c equals c. Now, like we did before, we want to slide this recipe card up until it covers the first rows, the top rows of this table. And our goal is to find what this third coefficient is in the expansion. So, the top entry of our recipe card, minus 2a plus 3b plus c, is going to cover 0. Our second entry, minus a plus b plus c, will cover the question mark, and then c will cover the 0. Now there's another missing entry right here, which would correspond then to the expansion of x plus y to the 3/2, and that would match up with a plus c. So we want to match up this 1 with 2a plus b plus c. So 2a plus b plus c is equal to 1. This system of equations can be solved for a, b, and c, and then we can determine question mark. That work is shown here, and the punchline is that question mark is the number negative 1/8. That would be the third coefficient in the expansion of x plus y to the 1/2. Using this method, Newton generated this expansion for x plus y to the 1/2, and then he used the same technique to expand binomials to any fractional power. But like you, Newton was skeptical about his technique. Does it make sense that the number of terms in the expansion is evidently infinite? And we could have made different choices than we did when we created and moved and then used that recipe card. Would every choice lead to the same expansion? Newton found a variety of ways to reassure himself that his technique was effective before he told anyone about his discovery, including squaring both sides of the expansion you see on the screen. He then sought a simpler way to find the coefficients in such expansions, and he found it. His results are today referred to as the generalized binomial theorem, and anyone interested in learning more can look this topic up by that name.